All right, good morning. Just a quick microphone check. Can you hear me? I'm on a new setup today.
Yes.
Okay. So, before we cast off into new material, can I answer any questions that you might have? Okay, so I will switch over to the PowerPoint slides and we'll do a quick recap and then we'll be off. All right. So this unit is all about steady state analysis of systems, both closed loop and open loop. And the highlights from Monday's lecture were that we defined the error for any system as the difference between the reference input and the output. You can do that either in the time domain or in the Laplace domain. They're equivalent. And then if you use the final value theorem in the Laplace domain, you can get the steady state value of the error by looking at the limit as s goes to 0 of s times your Laplace error signal. And so our first exploration was with a couple of simplifying assumptions. That was, we're going to assume unity feedback. And the conclusion from last lecture was unity feedback is a nice thing because it means that the signal that your controller is acting on is the true error signal. If there's something other than a 1 in the feedback path, then the output of that summing junction is no longer the error signal. It might be something vaguely useful, but it's not the thing that we want to minimize. Okay, so we assumed unity feedback, we assumed the disturbance was 0, and we assumed the reference was a unit step. And based on those assumptions, we kind of narrowed it down to two cases. You could have the lowest order coefficient in your denominator polynomial of your forward path transfer function could either be 0 or non-zero. Now that's super opaque how to say it that way, but the conclusion was that if that coefficient is 0, that is equivalent to there being a pole at the origin of that forward path transfer function, which I'm calling G. Okay, and then the last tidbit was we call poles at the origin integrating poles, or just integrators. Okay, so let's see. Yeah, that should work. Okay, so here we go, new material. So at the top, we have basically this general case, well, general insofar as there is still unity feedback assumed. There is still capital N integrators in the forward path transfer function, and there is still 0 disturbance assumed. So I say it's general case, but that's not true, let's be honest. This is the case where there is an arbitrary reference input R, but all of the other things are still assumed to be simplifications from the last slide, okay? So in this case, in this subcase of a subcase, we have this term called system type number. So the type number, and it's a very non-descriptive name, but I swear that's the official name. The type number of a system is the number of integrators in that forward path. So let me see if I can get the pen here. Yeah. So this number n and that number of integrators, that's the same. So common examples of type numbers are type 0. That would mean no integrators in that forward path transfer function. You could have type 1, type 2, type 3. The integers go on and on and on. The more integrators you have in that forward path transfer function, this is not something we prove, but it is a fact that the more integrators you have in that transfer function, the better your steady state error will be for a wider variety of reference inputs. Okay, so I usually go through another example, but I'm trying to give you a less mathematical feel for this and a more intuitive feel. We'll see how this goes. But the idea is it's rare to talk about a negative type number system. That would mean a system had a negative number of poles at the origin, which, I mean, if you think about it, is you could do that. A negative integrator would mean a differentiator, would mean a 0 at the origin. But let's not go there. Let's start our table at n equals 0 and count upwards. Okay, so if there are no integrators in this forward path transfer function, that is equivalent to this number a0 being non-zero. Okay, that was what we showed on the last slide of last class. And on the slide before that, we showed that in that case, the error steady state, the steady state error, is given by this ratio. And if you do something fancy, you can pull out an a0 from that expression, and you can write it like I have here. Okay. So let's recap what that means. For a type 0 system, if a reference step is introduced, the error in steady state will be a constant non-zero value. Okay, so what would the picture look like here? Can I erase? Yes. So the picture in this particular case, the input is a unit step. The error is going to be, well, let's call the error positive. So here's your R of t. And if error is r minus y, then that would mean that y is going to do whatever it does, and it's going to settle out to some value down here. Right, so it's important that I'm only talking about the graph from that point onwards. I'm only talking about the steady state value of these signals. So that's why I'm free to draw my random squiggles in the transient, because I'm not talking about that. So for a type 0 system, if a reference step is introduced, the output will settle at a constant value, but it won't settle at the right value. Okay, and the distance it settles is given by this value, the distance from the input. Now, let's contrast that with the next column over in this table, which says take the same type of system, a same 0 integrator system, and instead of introducing a step, let's give it a unit ramp. So here's our reference signal. If the system cannot track, and that's the verbiage we use to say how does its steady state performance work. If a system can't track a step, do you think it would be able to track a ramp?
Probably not.
Probably not, right? The step, if you think about it, it's being pretty nice to the system. It's got an instantaneous change, but then it doesn't change after that. Whereas the ramp is continuously changing and running off to infinity. And so we get this phenomenon here that the error in steady state actually diverges. So I want you to see that there are actually a couple different ways that this could happen. The more common way is if that is your response. So remember, the error in this graph is the difference between the R curve and the Y curve. So this is the error signal. And if these two rays, or these two curves, don't end up parallel, then the error blows up. The limit as time goes to infinity of this error difference is infinite. Okay, so that's the more common case. The other case is if the output ends up being a constant, then that also goes to infinity, if you look at the difference between that constant line and the ramp line. Okay. And so that pattern continues. The more complicated the input, i.e. the higher polynomial order of the input, the harder it is for the system to track. So this pattern continues for arbitrarily complicated polynomial inputs. Any questions on that? Because the rest are kind of wash, rinse, repeats of that, and I want to make sure everyone gets the little pictures I drew.
So what you're saying is that if there's not an integrator, then it ends up at a constant from a step, but it doesn't have any way to know that it's not at the right spot? That's
right. So the lack of an integrator you can think of as because this forward path transfer function acts on the error signal, if, great. Can I undo that? Nope. All right, sorry. Since this is the error signal, because we're guaranteed unity feedback here, guaranteed by way of assumption, you can think of this G system, you can, if you like, you can even do something like this. You can split off the integrators that you have. So you can also think of this as this going into an integrator, and that goes into G prime, where G prime is G without that pole at the origin. Right, so that's an equivalent way of thinking of this. So in the presence of an integrating pole in G, you can think of the error being integrated over time and then fed to a new system, i.e. the system without that integrator. And so if the error builds and builds and builds, then if we integrate that error, then we'll get something that even larger, and the system can respond to that. If we don't have an integrator, then exactly what you said is true. Then the error can be constant, and the system will have a non-unity gain to that constant, if you like.
What if the transfer function has a very like it damps out very quickly? If it's driving it towards 0, would it still have the error steady state equal to infinity for a ramp function?
Yeah, so I think it is conceptually difficult to hold two things in my mind, at least. That there is this G transfer function that I'm talking about, but there's also the entire closed loop transfer function. So the closed loop transfer function from R to Y, which as the class goes on, I'm going to end up calling that capital T. This is what, G over 1 plus G? And so when you talk about the system being fast, I think you probably mean that this system is fast. And that's not the system that I'm actually talking about here. I'm talking about the presence or absence of integrators in this subsystem, and I'm not at all talking about the speed. Because if you think about it, and like we talked about how poles that are far from the origin are fast and poles that are close to the origin are slow, you can't get any closer to the origin than a pole at the origin. So in some sense, an integrating pole is the slowest possible pole imaginable. I'm not sure if I answered your question. Go ahead and tell me if I didn't.
I feel like that does answer the question.
It's a rough morning here. Okay, hey, there we go. I just went to the next slide. Okay, sorry. Okay, now we're back to the slide that I want to talk about. Let's talk about a system with one integrator. So this is one integrator in G, not T, the closed loop transfer function. Okay, so the result from last lecture was that if that A naught term coefficient is 0, then the error in steady state is 0. And if A0 is 0, then that's equivalent to having one integrator. And so this is what we proved last time. So if we increase the order of the input, that is, instead of a step, we have a ramp, then we get this phenomenon that a ramp input to a type 1 system, so here's that same one-to-one ramp, will produce a constant error in steady state. Now, what would a constant error in steady state look like for a ramp?
A parallel.
Exactly, it has to be parallel. So this distance is given by that value in steady state. Okay. Now you can make that small. You can make it small either by making A1 small, or you can make it small by making B naught big. In particular, if A1 were equal to 0, we haven't talked about A1. Remember, A1 is the second lowest coefficient of the denominator polynomial of G. If A1 were 0, what kind of situation would that describe? Could you go through the analysis on the slide prior to this and tell me what would happen if A1 were also 0?
Would the two lines be on top of each other?
Yeah, so the error would go to 0. The input and the response would end up lying on top of each other. Let me go back here and show you what I'm talking about. So to go from this line to this line, that we use the knowledge that we're setting A0 to 0. To go, what if we also said, and what if A1 were 0? Well, then this term goes away, and now the lowest order S coefficient, S term here, has two S's, which means what we could actually do is pull out two S's. Knock all these down. So what we're doing here is we're chopping off terms from the denominator polynomial, and in so doing, we are buying more and more integrators. Okay, so this is the process that I want you to buy, that if A1 is 0 and A0 is 0, then we're no longer a type 1 system. And guess what? We become a type 2 system. Okay, and that's one of the reasons why that a type 2 system has 0 steady-state error due to a ramp input. Okay. So I love this table. This table is, let me admit, this table is of limited use. It's of limited use because it assumes unity feedback. It's of limited use because it assumes the disturbance is 0. But if you are looking to talk about the error due to a reference input in a unity feedback system, this table is priceless. Because let me see if I can clean things up here. That's not what I want. Let's see if I can erase the pen. Look what's happening here. Everything below the diagonal, they're all zeros. And 0 is good or bad in this context?
Good.
Good.
Yeah, we want small errors, and you can't get any smaller than 0.
Professor,
Yeah, go ahead.
I was looking at a pattern. I just wasn't sure if it was right. So I'm noticing, like, when n is 0, the 1 over s ends up being a constant. And then when n is equal to 1, then for the value below, like the steady state would be in 0 for like the step. And then the next one would be like a constant. And then if n equals 2, that happens for like 1 over s squared now. And then the 1 over s cubed term would then be a constant. Would that repeat? Like, if, like, let's say n was equal to 3, would the 1 over s, I guess, to the 4th, would that be a constant?
Yes.
And then, like, all the previous terms, like 1 over s cubed, 1 over s squared, 1 over s, would those be the steady state being equal to 0?
That's exactly right. Yes, that's the pattern I want to highlight here, is that this table, this array, has basically 3 characters. There's the stuff below the diagonal, which is all like excellent performance. There's the stuff above the diagonal, which is all terrible performance. And then there's the stuff on the diagonal, which is meh. But exactly right. So all of these rows keep going, and all of the columns keep going, and that pattern absolutely continues. So what we're saying here is that for a type N system, you can track inputs of type N and below. Now that is a kind of a loose statement, because you'll notice that these powers are one offset from the ends that they correspond to, if you like. But remember what it would mean in the time domain. So this would be u of t, which you can think about as t to the 0 u of t. A ramp would be t to the 1 u of t. A parabola would be something like, what, t squared u of t. And so this is what I want to point out. A type 0 system and a time domain input to the 0th power have this kind of finite error character. A type 1 system and a time domain input to the 1st power have this same finite error character. Whereas if you were to go down in type number, you get worse performance. If you were to go up in type number, you get better performance. If you were to go lower order input, you'd get better performance. If you were to go higher order input, you'd get worse performance.
Do these only work for this exact things like 1 over s squared, or would it also work for something like 1 over s squared plus 1?
Do you mean 1 over s squared plus 1, or do you mean 1 over s squared plus 1?
The bottom one.
They only work for these particular inputs, these 1 over s squareds.
And isn't that because they're integrators? So it has to be at the origin. So the other one, this is a pole.
So if your input, if r of s looked like this, one of the main problems is this is a sinusoid. This is sine t. So talking about the error when the input is a sinusoid is problematic for reasons that we've talked about already. The other, so maybe you're thinking this is not that useful. When have I ever going to see exact inputs like this? But I want to also point out that linear time invariant systems obey the superposition principle. And if we talk about the output of these systems being the sums of the outputs due to the various inputs, you can always decompose. Well, you can sometimes decompose if your input in the time domain has both a step and a ramp character. Then you are free to model this as t to the 0 plus t to the 1 u of t. Yeah? Then you would get some error due to the step, you would get some error due to the ramp, the total error that you would then sum them, because this is an LTI system and it obeys superposition. So again, it does appear to have limited use, but as long as you know that you can take linear combinations of these input types, then that allows you to model various input signals as sums of polynomials. You will rarely see this table presented in this way. Usually it's presented in the way that I'm going to go to the next slide and show you. And that is given these quantities in terms of the G transfer function. So this is the exact same table as we had on the last slide. It's just presented in the way that it's more commonly written. This is what you'll find in your textbook. Well, let me amend that. Your textbook replaces this with the variable k sub p, and it replaces this with the variable k sub v, and this with the variable k sub a. And what these k's are, they're known as static error coefficients. Kp, kv, ka. And the reason that I don't particularly like this notation is because you run out of letters. Like, how would you talk about the error in a type 3 system? You'd have to make up your own static error coefficient. So I prefer to think about it in terms of these limits, which is exactly how these static error coefficients are defined in the textbook. This is the limit as s goes to 0 of g of s. K sub v, or the velocity static error coefficient, is the limit as s goes to 0 of s g of s, et cetera, et cetera, et cetera. I prefer to think of this as, if I have a type 0 system, then I want to take the limit as g goes to 0, and I want to multiply that g by s to the 0. So this is how I think of it. A type 0 system means multiply g by s to the 0. A type 1 system means multiply g by s to the 1. A type 2 system means multiply g by s to the 2, and then take the limit as s goes to 0. The one piece of this pattern that breaks the pattern is this first upper left-hand corner. Everything else down this diagonal looks like 1 over some limit. This upper piece here is different because it has this 1 plus out there. So I don't want you to overgeneralize. Okay. So again, if I have a type N system, then I know that it can handle low order inputs perfectly. It can handle high order inputs terribly, but the one quantity that I actually need to calculate, I can get if I know that number. Right? It's 1 over limit as s goes to 0 of s to the capital N times g of s. Let's see an example. Okay, so what we're going to do is we are going to compare the error performance of 2 alternative designs. So the idea here is that we have a single object, a single process, or a single plant is the controls term that we'd like to control. So note that the rover block is the same in these 2 cases. Now the difference, primary difference, is in the topology of these 2 controllers. In A, which I'm going to call the open loop system, particularly because there is no feedback loop, and open loop I'm going to abbreviate to be OL, FYI. The controller has been designed such that the zeros of the controller will cancel the poles of the rover, making the effective poles of the system equal to the poles of the controller. Okay, so that was why this controller has been chosen, is because someone decided that the transient performance is better if the closed loop pole, if the poles of the system are the roots of s squared plus 4s plus 5. In the closed loop topology, the controller is significantly simpler. The controller is just an amplifier. Now, that's not to say that this is simpler overall, because we need some way to physically feed back this signal and then take the difference here. But so there's no free lunch, is what I'm trying to say. But that's where these 2 topologies come from. So I want you to imagine that we are in a design review meeting, and one team says we should use open loop because then we don't have to buy this expensive sensor with unity feedback. And the other team says, no, we should use closed loop control because it allows us to build a simpler controller. And as we'll be the adjudicator between those 2 teams. And what we're going to do is we're going to determine which of these 2 topologies, open loop or closed loop, gives us better steady state error performance. Okay, that'll be the deciding factor in this fiction that I'm telling you. The backstory is fiction. The math is not fiction. Okay, so first things first, if we're going to compare apples to apples, let's decide on the value of k. So let's stop doing that, clear that. So the transfer function from R to Y in the open loop case. So what am I going to do with this disturbance signal here? If I want the transfer function from R to Y, what should I do with capital D?
Set it to 0.
Set it to 0, which means the summing junction becomes just a straight pipe. Excellent. So then I just multiply the controller block by the rover block. The numerator here cancels the denominator there, and I just end up with k on s squared plus 4s plus 5. Okay. The only trick there was to know what to do with the D signal. But because the transfer function from R to Y, it's implied the output Y due to the input R set the other inputs to 0. That's superposition. Okay, so in closed loop, we do the same trick. We set the D signal to 0, which means the forward path is k over s plus 1, s plus 3. And the feedback path is unity. Ooh, that's a good sign. We get these nested fractions that are the hallmark of this course. And we simplify this down. We get s squared plus 4s plus 3 plus k. Okay. So is there a k that makes this transfer function equal to that transfer function? Yes. Let k equal 2. Then the denominators match, the numerators match, everyone's happy. Okay, so for the rest of this problem, we're going to let k be 2. And the reason for that is that makes the input-output transfer function of these two systems exactly identical, right? If you were to place a black box over either of these systems, both of these systems, when k is 2, they should act the exact same. Now I'm going to follow that up with kind of a non sequitur. I am going to, in the right-hand margin here, I'm going to work out the transfer function from D to Y for both of these. We're not going to use it yet, but we're going to use it a couple slides from now. So if I want the effect of the disturbance on the output of the open loop system, the complementary statement to what we just said is now we're going to let R be 0. If R is 0, this signal is 0. If that signal is 0, then from D to Y, the only difference is this rover transfer function. So I hope you're starting to see the downside of open loop control. It's because all the money that you just spent building this fancy pants controller is completely subverted if the disturbance comes in, right? The disturbance has no idea how much money you spent on your controller, and it's just going to play havoc. So anyway, that's foreshadowing. I don't know if it's foreshadowing if I tell you exactly what's happening. Let's do the same analysis down here. Let me redraw the system to make it a little bit nicer. So disturbance comes into a plus-plus junction, and then we've got the rover, and then we've got Y. Y comes down and gets fed into a -1 from this summing junction with R, and then a K, and then into that summing junction. So I think the trick I want to pull is I want to move that -1 up there to make this a negative feedback loop. Then I can use our standard feedback loop reduction rules and just say this is the rover transfer function in the forward path over 1 plus k times the rover transfer function in the bottom. Okay, if you simplify that, what do you get? You get 1 on s squared plus 4s plus 3 plus k. Okay, so these disturbance transfer functions we're going to handle in a couple minutes. Let's go on to the next slide where we're going to make use of these transfer functions. So we're told that a reference step is input, and we want to compare the steady state error between the two systems. So let's do open loop first. Here's a question. Can I use the steady state error table to answer the open loop error question?
You can't factor out an S or an S squared, so you can't.
Right answer, wrong reason. I can't use the steady state error table because the feedback in the open loop system, you can think of it as a 0 block. Yeah? And those steady state error tables are only applicable to unity feedback systems.
Mm-hmm.
Yeah. So we can't use the steady state error table, which is a bummer because we spent basically the entire lecture talking about it, but we can go back and recall the original definition of error, minus y of s. We're told, well, we can also do this trick where we factor out the r. and we're told what R is. We're told that R is a step. So we also figured out what y over R is. That was from the last slide, 2 over s squared plus 4s plus 5. Okay, so when taking these limits, and again, we're going to take a limit because of the final value theorem, it's nice if all of your fractions are combined. So I'm going to combine the square bracketed thing here to be s squared plus 4s plus 5 minus 2 over the same denominator. Then the error steady state open loop is going to be the limit as s goes to 0 of s times that error signal. So the s and the step s will cancel. And then I'm going to let all the other s's go to 0. So I end up with the answer 3/5. Okay. So if I command this rover to go, I don't know, 1 meter forward, the rover will actually only go 2/5 of a meter forward. That's what we just showed in the open loop design. In the closed loop design, let's ask ourselves, can we use a steady state error table? The answer is now yes, because we have unity feedback. To use the error table, you have to determine 2 quantities. What type of input do you have, and what type of system do you have? So it's clear we've got a step reference. Now, let's answer the question, what type system do we have? How many integrators are there in the forward path transfer function?
2.
Try again. I
None.
see a pole at -1, a pole at -3, end of story. I don't see any poles at the origin here.
Oh, 0.
None.
Right. There are 2 poles, and it's a second order system, but this is a great point, and I'm so glad that someone volunteered the wrong answer, because this drives home the point that the type number and the order of a system are 2 different things. They're 2 separate concepts. Now, okay, your order can never be any lower than your type number, but let's forget about that. The order of a system is not the type of the system. The type of the system is the number of poles at the origin. In this case, we have a type 0 system. If we have a type 0 system, then the error in steady state is given by that first, the upper left-hand entry in the table. And so the relevant quantity I have to calculate here is what is g of s as s goes to 0. So the limit as s goes to 0 of g of s is what? It's k over s plus 1, s plus 3. I believe that is, if I let the s's go to 0, I get 2/3. So plug that in there, and we get 1 on 1 plus 2/3, which is 1 on 5/3, which is 3/5. So halfway through this design review meeting, and we have established that if both of the R to Y transfer functions are identical, then both of the R to Y errors are identical. That's not terribly surprising. I'm sorry that this is a bit of a letdown. Functionally what this means is that we can't use error due to a reference input to distinguish these 2 systems, to distinguish these 2 topologies, because they're identical. So maybe we need to analyze the error due to the other input, and that's where we get to the last slide of it today. But any questions before I move on?
I got one simple question.
Yeah, go ahead.
For the open loop, how is it because the denominator order was s squared, that's why you have to take the limit of s approaches 0, s times e of s?
No, so this is just a general statement. This is the final value theorem. If I want the final value of this guy in the time domain, I have to look at s times its Laplace transform as s goes to 0.
Okay, thank you. I just
Yeah,
forgot
sure.
this final value.
Okay, cool.
Oh, I had one question really quick. For the closed loop system, it's type 0, just to reiterate, because there are no poles at the origin.
Correct. Correct. The G of S for our closed loop system was K on S plus 1, S plus 3, and the pole zero map looks like that. But importantly, there's nothing there.
Okay, thank you. Thank you.
Absolutely. All right. So now we are going to analyze what does the error do when the disturbance signal is a step. So think of this as, I don't know, if this is the rover on Mars, there could be some kind, I guess wind wouldn't really. Let's say that there is some wind or some, no, we'll do an alien. Say an alien comes up to the rover and pushes it, which is a disturbance signal. So how much error is going to be introduced due to that alien push? That's the question we're asking here. So in open loop, we want to find the error in steady state. We can't use the error table for a number of reasons. Number one, it's an open loop system, so it's on unity feedback. Number two, the reference input is 0, which means that there is no column for a reference input of 0. So this is why this slide is actually the point of this whole exercise. The error signal is still what you want minus what you have. Now this is the $10,000 question. What should R of S be?
If we're going to do superposition, should it be 0?
That's exactly right. So if we're doing superposition, and if we're saying that the output is only due to the disturbance, the error is simply the negative of the output. Okay, so if there's no reference input, is the output 0? Like, is this just a trick question?
Well, there's going to be some sort of disturbance that causes it to be something other than 0.
Good. There will be output. And I like to think of it as the disturbance signal times the disturbance to output transfer function, right? So,
Could you clarify as to why the reference is 0 again? I kind of missed that.
so we are told that we want to find the error due to a disturbance step. The only way to find the error due to one input is to set the other inputs to 0. That's the this notion of superposition that I've been harping on.
Gotcha, yeah.
Okay, so what do we got here? We're told that the disturbance is a step, and this is where I'm going to use our results from 2 slides ago, where we worked out the disturbance to output transfer function. So this was 1 on S plus 1, S plus 3. Therefore, the error in steady state is going to be the final value theorem applied to that signal. Which looks like -1 on 3. Okay. So if the alien pushes with a unit force in one direction, the rover will end up moving -1/3 of a meter from where we thought it was. Is that good? Is that bad? Don't know yet. Let's have something to compare it to. In the closed loop system, the error is still what you want minus what you have. And this is where that notion, that thought process, what you want minus what you have, I think pays dividends, because what you want is 0, right? The system is sitting still. I'm not telling it to do anything, and yet forces beyond my control are moving the system. I would like for the system to not do anything, but you can't always get what you want, so let's see how far off we are. So this looks like the same expression. That is, how does the system translate disturbances to output? Because now any output, any value for y is error. because we desire nothing to happen, and yet something's happening. So again, we get the step disturbance, and here is where the closed loop topology pays dividend, because we have a different d to y transfer function. This is from 2 slides ago, the transfer function from d to y in the closed loop system. So error steady state now, again, is final value theorem applied to that signal. Which ends up being -1/5. So the conclusion here is that in open loop, the error in steady state due to a disturbance in magnitude is larger than in closed loop. So yeah, don't let these negatives throw you off. Mostly we're talking about sizes of errors, not necessarily directions of errors. So this is probably the conclusion of that design meeting. It would say the two topologies are equivalent for reference errors, but the two topologies are, the two topologies are the same for reference errors. But in terms of error due to a disturbance, the closed loop system is superior.
Does this mean that if you have like the same disturbance for both, then the disturbance for a closed loop will be -1/5 times as large, or like -1/3 times as large?
So it is true that if the step scales, so if this is u of t versus 5u of t, then the steady state error also scales, because this is still a linear system and we can get that scaling factor. So yeah, I think that was what you're asking. If the step disturbance is scaled by the same value on both systems, then that scaling factor will scale these two scalars, and that preserves this ordering, that the error in steady state in open loop is bigger than the error in steady state due to the closed loop. Broadly, this falls under the category of what's called disturbance rejection. Which is one of the main goals of a control system. So the more your system can reject disturbances, the better of a control system you have on your hands. Okay. And this result we got from this particular kind of toy example, but it's actually more true in general, that you will always get, for a reasonably good closed loop controller, you will always get better disturbance error in a closed loop system than in an open loop system.
-1/5 and -1/3, they both seem like kind of similar numbers. Does that mean that they're both kind of like similarly bad at it? Because there's still some error, like, because if you have like a ramp, then it's still gonna be just as bad, wouldn't it?
Absolutely. I'm not saying that this is the best possible controller topology for this system. In particular, if you wanted to zero these numbers out, like if you wanted to make these numbers 0, you'd have to go way back to the drawing board, and you'd have to put an integrator in your controller. Right? That would increase the type number of the closed loop system. That would buy you 0 error due to a step.
Okay.
There are consequences for this. So I think a lot of students leave this unit of the class thinking, okay, integrators are the answer. If I have an error problem, I'm just gonna throw integrators at it. And I understand where that inclination comes from, but I want you to hold on to that thought, because the implications for closed loop stability, there are gonna be a trade-off. You can't always just throw integrators at your problem, because you'll end up moving the problem to make the system unstable. Okay, so for time being, ignore that. Just think about how integrators can improve your steady state error performance. We'll talk about stability starting on Friday. And that actually brings us to the end of the steady state analysis unit. So this is only a 2-day unit. Cool. Thank you, everyone, and I will see you in office hours.